My name is Tim, and I will be presenting our work on expectation programming. This is joint work with Adam Golinsky, Luke Ong, and Tom Wainford. Calculating expectations is at the center of many scientific workflows. Among many other things, its applications include calculating the expected cost of a decision, the probability of rare events, or estimating scientific constants from data. For the rest of this talk, we assume the following setup. Given some observed data y and latent variables x, we are interested in the expectation of our target function f with respect to the posterior p of x given y. Currently, most probabilistic programming languages focus on providing algorithms to automate inference. However, this ignores valuable information about the target function. Instead, we propose a framework that directly automates estimating expectations and that can incorporate information from the target function f. Our framework is built on top of Turing, so let us first look at how users would conventionally estimate expectations in Turing. The general workflow is similar in other languages. Turing models are normal Julia functions which are annotated with the model macro, and the tilde operator can be used to define random variables. Here we define a model with latent variable x and observed data y. Furthermore, outside of our Turing model, we can define our target function f. We can then obtain samples from the posterior using one of the inference algorithms implemented in Turing. Here we generate 1,000 samples with nuts using Turing's sample function. Once we obtain the samples, we can form a simple Monte Carlo estimate of our expectation, which is done by applying our target function f to each posterior sample and then taking the mean. We would like to make this workflow more efficient by incorporating information from the target f. There are several options to use information from the target function to better estimate expectations. In this work, we will focus on using the framework of target-aware Bayesian inference, or TABI in short, which we will describe on the next slide. However, in principle, there are other options to include information from f, such as control variates or other variance reduction techniques. We hope that this work inspires others to think about how probabilistic programming languages can exploit information from the target function. So the main idea of TABI is to split up the expectation into three terms, which can be viewed as the normalization constants of three different densities. So normalization constants Z1 plus and Z1 minus contain information about the target f. For more details, we refer to the TABI paper. Now that we have seen a technique to exploit target information, we can think about how we could exploit target information in probabilistic programs. In the end, many practitioners of Bayesian statistics use probabilistic programs to conduct their analysis. Our key insight is that we can interpret probabilistic programs as defining expectations over their return values, and then use this interpretation to generate target-aware inference algorithms. Previous work has interpreted probabilistic programs as defining expectations over their return values, but they have not used this interpretation to generate target-aware inference algorithms. Concretely, we introduce a new framework built on top of Turing called EPT. Users can use the same syntax as in Turing to define probabilistic models, but by changing the macro from add model to add expectation, the program is interpreted as an expectation. This program here defines the same expectation as the previous Turing example. Note that now we define our target function inside the model as part of the return statement. In our framework, the estimate expectation function, as the name suggests, allows users to directly estimate expectations. The function takes as input the expectation we defined using a macro with a specific value for the observed data. And it allows users to specify the method that is used to estimate the expectation. In this case, we use the TABI method introduced earlier, and we use a Turing implementation of a yield importance sampling as a marginal likelihood estimator. So what exactly is the expectation macro doing? It generates three Turing models from the original program, one model corresponding to each of the densities in the TABI estimator. This slide shows the transformations for our example program. The user-defined expectations on the left and on the right are the three created Turing programs. The changes in the program source are highlighted in blue. The programs representing the densities are valid Turing programs. This means any inference algorithm in Turing that provides marginal likelihood estimates can be made target-aware with our framework. We don't need to change a single line of code in Turing itself. Finally, to show the efficiency of the target-aware approach over the non-target-aware approach, we conduct experiments on an SIR model used in epidemiology. We measure performance based on relative squared error and effective sample size. Here, the target-aware approach is in blue. We can see that by incorporating information from the target function, performance improves by several orders of magnitude. Thanks very much for watching.